All right, let's revisit the Kenya's neighbors Pima Indians diabetes case. But now what we're gonna do is we're gonna add dimensionality reduction. In this case, PCA or principal component analysis. This, as you remember, was a low dimensional problem. We only had 8 features. Yeah? So PCA is probably not gonna be very effective. But what I would like to see is that you have a good grasp of what it means to add a PCA analysis to your code. And you will see that it's actually quite simple. Yeah. So if we take a look at the first code cell, then you see that we just need to import PCA from sklearn. Okay. All the rest is gonna be practically staying the same. Yeah, so let's just drill down here till we've split the data frame and we imported the train test split. Then we've done the scaling, and after the scaling is a good time to talk about PCA, because we know that in order for PCA to be effective, you need a mandatory mean normalization stage. Yeah, so that's exactly what we did here in line 37. We did mean normalization and brought the standard deviation to 1. Yeah. So now we're gonna add actually the PCA code. Yeah. So this is basically these 4 lines. You define PCA, you choose your numbers of dimensions. In this case, we're gonna go to 2 dimensions, and we come from 8. And then basically you're gonna fit the PCA and doing all the calculations on the training set X train. And then you're gonna transform both X train and X test together. Yeah. So keep in mind that for X test, we do not do a fit. Yeah? We want things to be as clean as possible. And then, of course, we can run a shape here. A shape tells us that there's 614 rows, and as we want it, there's only 2 dimensions. So here you can see a plot of the data along PCA1, PCA2, and you see the data is not easily, I would say, separable, especially in 2 dimensions. Yeah. But that's basically it. And now what you do is you just continue with what we did last time. The only thing you need to do is to change the parameters to PCA parameters. Yeah. Especially for the axis. Yeah, so here there's nothing to change. We can just run. Here as well, we can just run. Here we need to change. You see X train PCA. The Y's we leave as is, and X test PCA. And here as well, X train PCA. Yeah. So let's run that cell and let's plot it. Here you see that now you get an optimum at 24. Yeah, so we look at 24 neighbors in order to decide on the label of a test point. So now we're gonna run it. Again, I changed the parameters to the PCA parameters, and I filled out the K, which is 24. So we run it, and you'll see that your accuracy is only 70%. That's lower than in the non-PCA case. Yeah. Which is not a surprise. I mean, PCA in this case will just give you less data. And this we can see if we print the explain variance. You see, if we add these 2 up, you have less than 50% of the original variance. And we've seen that our target should be roughly above 85 and ideally 99%. So I expect the confusion matrix is gonna be a little bit less good. Yeah. So you see only 25 true positives, true negatives went from 90 to 83. Your false positive went up, and your false negatives went up. Yeah. So your recall dropped a little bit more. It's less than 50% now, and even your precision came down. So not very good. And the curve as well. If we plot the curve, if you would put it next to the non-PCA case, you would clearly see that the area under the curve has gone down. And here we prove it is. Here we go. Here we prove it is 74.4%. Now, how many blocks of codes do we have? Let's do a quick restart and run all. Here we go. It's 26 lines of code, yeah, blocks of code, yeah, which is actually quite simple. Huh? Remember, we had about 20 blocks in the non-PCA case, so adding PCA is not that difficult. Okay, that was it. See you next time.